In the previous video, we learned about the structure of the iron-carbon diagram. In this video, we will now take a closer look at the microstructural processes during the solidification and cooling of steels. The iron-carbon diagram summarizes the different phase ranges once again. Although steels are basically ferrite and cementite at room temperature, the cementite is arranged differently in the microstructure depending on the carbon content, which in turn affects the properties of the steel. The formation of the different microstructures is therefore discussed in the following. To do this, the delta phase mentioned in the previous video is first neglected in the phase diagram. Furthermore, for the sake of simplicity, we assume that the carbon is completely insoluble in the alpha iron. In this case, the alpha phase region at the bottom left of the diagram is neglected. The end of the gamma-alpha lattice transformation then always occurs at 723 degrees Celsius, regardless of the carbon concentration. The iron-carbon phase diagram can in principle be divided into two parts. The upper part shows the lenticular solidification region typical of solid solution alloys. Any steel, regardless of its carbon content, will therefore initially solidify as a solid solution alloy. The carbon is completely dissolved in the face-centered cubic gamma iron immediately after solidification. The lower part of the phase diagram shows the typical lines of a mixed crystal alloy whose components are not soluble in each other in the solid state. And indeed, the carbon is not soluble in the alpha iron. Only in the gamma phase is there complete solubility. In mixed crystal alloys, this region corresponds to the melt, in which complete solubility is also initially present in the liquid state. In the left two-phase region below the liquidus line, the base material starts to precipitate from the melt, and in the right two-phase region the alloying element starts to precipitate. Similarly, in the left two-phase region of the iron-carbon phase diagram, the base component ferrite begins to precipitate out of the austenite due to lattice transformation, and in the right two-phase region the alloying component carbon begins to precipitate out of the austenite as cementite due to no longer complete solubility. There are therefore analogous processes between the solidification of a mixed crystal alloy and the formation of the steel microstructure. The main difference is that these processes take place in the already solidified state of the steel, rather than in the liquid state. The formation of the steel microstructure for a carbon content where the lines meet in a common point also shows strong structural similarities to a eutectic. Because of this similarity, this point is also known as a eutectoid point. The term eutectoid literally means similar to a eutectic. In the following, the microstructure formation of selected steels will be explained in more detail. We will first consider a eutectoid steel with a carbon content of 0.8%. After the steel has solidified in a temperature range between 1480 and 1380 degrees Celsius, resulting in the formation of austenite, it finally undergoes the gamma-alpha transformation at a constant temperature of 723 degrees Celsius. The face-centered cubic lattice structure of austenite now begins to transform into the body-centered cubic lattice of ferrite. The carbon that is no longer soluble in the ferrite lattice is precipitated as cementite during this lattice transformation. Because the temperature is relatively low at 723 degrees Celsius, the precipitated atoms are slow and cannot travel long distances. They therefore precipitate directly from the lattice and accumulate in a lamellar structure. When the austenite lattice is finally completely transformed into the ferrite lattice, the carbon is completely precipitated from the iron lattice due to its insolubility in ferrite. The former austenite grains have transformed into ferrite grains with embedded cementite lamellae. This process also causes the grain boundaries to change, transitioning from a polygonal structure to a rounded form. The lamellar phase mixture of ferrite and cementite is also referred to as pearlite or more commonly as eutectoid. This micrograph shows the microstructure of a eutectoid steel under a microscope. Note the dark cementite lamellae embedded in the white, almost carbon-free ferrite grains. In the following, we will focus on a steel with a higher carbon content than the eutectoid steel just described. Such steels are also referred to as hypoeutectoid steels. A few basic remarks are made on this. Although carbon is relatively soluble immediately after solidification, it is in principle not infinitely soluble in the austenite lattice. This is because the carbon atoms are relatively large compared to the free octahedral sites in the centers of the face-centered cubic unit cells. This leads to lattice distortions in the vicinity of the intercalated carbon atoms. Within the distorted lattice region, no more carbon atoms can be incorporated since the lattice distortions are too strong. Only at some distance further carbon atoms can be incorporated again, when the lattice distortions have settled, so to speak. As the temperature drops, the lattice vibrations decrease. As a result, the space within the unit cells becomes smaller. Therefore, fewer carbon atoms can be incorporated into the austenite lattice. The solubility of the carbon atoms therefore decreases with decreasing temperature. The maximum solubility is 2.06% at 1147 degrees Celsius. With the solubility limit drawn in, the maximum soluble carbon content in the austenite can be determined for any other temperature. Thus, the maximum solubility of carbon at a temperature of 1100 degrees Celsius is about 1.9%, while at 950 degrees Celsius only about 1.4% carbon can be dissolved. At 800 degrees Celsius, the solubility has even dropped to about 1%. Due to the limited solubility of hypereutectoid steels, further microstructural changes occur when cooling below the solubility limit, as the steel then obviously contains more carbon than the lattice can actually dissolve. Using the example of the hypereutectoid steel with 1.4% carbon, the structural changes that occur are explained in more detail in the following. In the temperature range between 1440 and 1260 degrees Celsius, the steel solidifies again as a solid solution alloy in the form of austenite. On further cooling to 1100 degrees Celsius, the austenite can dissolve a maximum of 1.9% carbon. However, as the considered steel contains only 1.4% carbon, the carbon is initially completely soluble. As cooling progresses, the solubility decreases. At 1000 degrees Celsius, the solubility has already decreased to about 1.6%. When the state point finally reaches the solubility limit at about 950 degrees Celsius, the austenite can dissolve as much carbon in the lattice as the steel has. In this case, 1.4%. However, if the state point falls below the solubility limit, then there is more carbon in the microstructure than can actually be dissolved in it. For example, the maximum solubility at 900 degrees Celsius is 1.25%, but the steel in question has a carbon content of 1.4%. The microstructure is therefore unable to dissolve all the carbon. The excessive carbon that can no longer be dissolved precipitates out of the austenite lattice in the form of cementite. The precipitation takes place preferentially at energetically favorable sites such as grain boundaries. For this reason, the precipitated cementite is also known as grain boundary cementite. As the temperature continues to decrease, the maximum solubility also decreases and more cementite precipitates at the grain boundaries. Thus, at a temperature of 800 degrees Celsius, only a maximum of about 1% carbon is soluble and therefore present in the austenite. The rest is precipitated at the grain boundaries. The carbon concentration in the austenite therefore approaches the eutectoid point with further cooling. Eventually, at 723 degrees Celsius, so much carbon has precipitated that the eutectoid composition of 0.8% carbon is just reached in the austenite. The austenite then behaves in principle like a eutectoid steel with 0.8% carbon. At a constant temperature of 723 degrees Celsius, the austenite begins to transform into the body-centered cubic lattice structure of ferrite, which is completely insoluble for carbon. In the process, the carbon is precipitated from the lattice in the form of cementite lamellae, as is usual during gamma-alpha transformation. Hypereutectoid steels therefore have a pearlitic microstructure at room temperature, which means ferrite grains with embedded cementite lamellae and additional precipitated cementite at the grain boundaries. This micrograph shows the microstructure of a hypereutectoid steel with 1.2% carbon under the microscope. The relatively broad grain boundaries of cementite can be seen. They appear whitish due to the special preparation of the sample to make the grain boundary cementite visible. The individual pearlite grains are very difficult to resolve under the light microscope and appear as brownish grains. In the following, the cooling of a hypoeutectoid steel with 0.4% carbon is considered. Solidification takes place between 1500 and 1450 degrees Celsius and the austenite structure is formed. Since austenite can always dissolve at least 0.8% carbon, hypoeutectoid steels generally have too little carbon to fall below the solubility limit. These steels therefore do not reach the solubility limit during cooling. The carbon in hypoeutectoid steels therefore always remains completely soluble in the austenite lattice. The microstructural transformation of a hypoeutectoid steel is therefore not determined by the solubility limit, as is the case with hypereutectoid steels, but by the onset of the gamma-alpha lattice transformation. In a hypoeutectoid steel with 0.4% carbon, the gamma-alpha lattice transformation starts at about 790 degrees Celsius. The face-centered cubic lattice begins to transform into the body-centered cubic microstructure at the energetically favorable grain boundaries. This lattice transformation spreads to the surrounding austenite structure during further cooling. Since the carbon can no longer be dissolved in the already transformed alpha iron, it is displaced from the body-centered cubic ferrite structure. However, the surrounding austenite can still absorb this displaced carbon due to the undersaturated state. Therefore, the carbon precipitated from the ferrite lattice diffuses into the adjacent austenite. In this way, the austenite becomes increasingly enriched with carbon during further cooling, which means as the gamma-alpha lattice transformation progresses. As is usual in two-phase regions, the chemical composition of the phases can be determined at the respective phase boundaries. The purple transformation line therefore shows the carbon content of the austenite. At a temperature of approximately 770 degrees Celsius, the residual austenite has enriched to approximately 0.5% carbon. At 750 degrees Celsius, the carbon content in the austenite has already increased to about 0.6%. With further cooling and progressive ferrite formation, the carbon content in the austenite gradually approaches the eutectoid point. At 723 degrees Celsius, the carbon content in the austenite has finally increased to 0.8%. The austenite has now reached the eutectoid composition. The austenite therefore behaves as a eutectoid steel and begins to transform at a constant temperature into pearlite with its typical cementite lamellae. Thus, hypoeutectoid steels show a pearlitic microstructure at room temperature, which means ferrite grains with embedded cementite lamellae in which the previously formed ferrite grains are embedded. This micrograph shows the microstructure of a hypoeutectoid steel with 0.45% carbon under the microscope. Note the white ferrite grains and the pearlite grains with cementite lamellae. In comparison, the next micrograph shows a steel with a higher carbon content of 0.6%. Accordingly, the pearlite content is higher in this microstructure. Let us summarize the microstructure formation of steels once again at this point. The actual solidification process in steels takes place independently of the carbon content, as in a solid solution alloy. Austenite is first formed from the melt. In the face-centered cubic gamma iron of austenite, the carbon is completely soluble after solidification. All further microstructural processes now take place in the solidified state. In a eutectoid steel containing exactly 0.8% carbon, the face-centered cubic austenite changes at 723 degrees Celsius to the body-centered cubic ferrite structure, which is insoluble for carbon. The insoluble carbon precipitates from the austenite in the form of strips. At room temperature, the microstructure consists of ferrite grains with embedded cementite lamellae. This phase mixture is called pearlite. In hypereutectoid steels with carbon contents above 0.8%, the insoluble carbon precipitates as cementite at the grain boundaries when the solubility limit is undershot in the phase diagram. This leads to a depletion of carbon in the austenite. Thus the carbon concentration in the austenite decreases as cementite is formed. Eventually, at 723 degrees Celsius, the carbon content in the austenite has reached the eutectoid composition of 0.8% carbon. Now, at a constant temperature of 723 degrees Celsius, the transformation of the face-centered cubic austenite into the body-centered cubic ferrite begins, with the carbon again being precipitated in stripes and the microstructural component pearlite being formed. In hypoeutectoid steels with carbon contents below 0.8%, ferrite precipitates from the austenite lattice below a certain temperature, as the face-centered cubic austenite begins to transform into the body-centered cubic ferrite structure. The carbon cannot dissolve in the ferrite lattice. The carbon therefore diffuses into the surrounding austenite lattice, which can still absorb carbon. This leads to an accumulation of carbon in the residual austenite. The enrichment eventually progresses until the austenite has reached the eutectoid composition of 0.8% carbon at 723 degrees Celsius. Pearlite is formed from the austenite. The processes involved in the formation of pearlite are always the same, regardless of the steel. The microstructure of a steel always consists of two phases, ferrite and cementite, whether it is a hypoeutectoid, hypereutectoid or eutectoid steel. Only the way in which the cementite is present in the microstructure, for example in pearlite or at the grain boundaries, differs. The determination of the exact microstructural proportions of pearlite and ferrite, or pearlite and grain boundary cementite, is explained in the following. In principle, the determination of the microstructural fractions of steels is carried out in the same way as for solid solution or eutectic alloys by using the lever rule. The lever arms must always be drawn up to the corresponding microstructure or phase boundaries. In the following, the microstructure fractions at different temperatures are determined for a hypereutectoid and a hypoeutectoid steel. For a hypoeutectoid steel with 0.3% carbon, the microstructure at 650 degrees Celsius consists of ferrite grains and pearlite grains. To determine the respective microstructural proportions, the lever arms are drawn from the considered state point up to the phase ferrite at 0% carbon and up to pearlite at 0.8% carbon. It should be noted that pearlite has a eutectoid composition of 0.8% carbon, and this concentration therefore represents pearlite. The imaginary buckets containing the microstructure components are now attached to the corresponding lever arms. The calculation is now made as usual using the lever rule, that is the quotient of the length of the opposite lever arm and the total length of both lever arms. For the steel in question, this gives a ferrite content of 62.5% and therefore a pearlite content of 37.5%. The solubility of carbon in alpha iron has been neglected in this calculation. At this point, the low solubility of carbon in alpha iron should be explicitly considered. In this case, the imaginary bucket of ferrite is not attached at 0% carbon, but at the intersection with the solubility limit, since in this case alpha iron has dissolved 0.01% carbon. This gives a ferrite content of 63.3% and a pearlite content of 36.7%. Therefore, even at this high temperature of 650 degrees Celsius, the solubility of the carbon in the ferrite has only a minor influence on the microstructural proportions. This is particularly true at room temperature, where the solubility of carbon in alpha iron is much lower. At room temperature at the latest, the low solubility can therefore be neglected. In addition to the microstructural fractions, such as pearlite and ferrite, we can also determine the individual phase fractions at room temperature, which means the percentage of cementite and ferrite in the overall microstructure. The term phase fraction should not be confused with the term microstructure fraction. The microstructural component pearlite consists of a phase mixture containing both the phase ferrite and the phase cementite. The procedure for determining the phase fractions is basically the same as for determining the microstructure proportions. However, it should be noted that the lever arms must then be drawn up to the respective ferrite and cementite phase boundaries and not up to the microstructure boundaries. Again, neglecting the solubility of carbon in alpha iron, the ferrite phase is at 0% carbon. The cementite phase occurs at 6.67% carbon because at this carbon content the microstructure is 100% pure cementite. Applying the lever rule, this gives a ferrite content of 95.5% and a cementite content of 4.5% in the microstructure. In the hypoeutectoid steel under consideration, the cementite is exclusively present in the pearlite microstructure in the form of lamellar cementite. Analogous to hypoeutectoid steels, the microstructural constituents of hypereutectoid steels can be determined. As an example, we consider a steel with 1.4% carbon at room temperature. As long as we again neglect the solubility of the carbon in the ferrite, we can draw in the state point somewhere below 723 degrees Celsius, since below this temperature the microstructure does not change anyway. Again, the lever arms are drawn up to the respective microstructural constituents. For pearlite, the microstructural boundary is again at 0.8% carbon. For grain boundary cementite, which is another microstructural constituent, the boundary is again at 6.67% carbon as this is pure cementite. Using the lever rule, this gives a pearlite content of 89.8% and a grain boundary cementite content of 10.2%. The steel microstructure itself consists of only two phases, ferrite and cementite. The phase proportions can again be determined from the respective phase boundaries. Again, we use the ferrite phase on the far left of the diagram at 0% carbon and the cementite phase on the far right of the diagram at 6.67% carbon. In this case, we obtain a ferrite content of 79% and a cementite content of 21%. In a hypereutectoid steel, the cementite is present both in the microstructural part of the pearlite as strip cementite and at the grain boundaries as grain boundary cementite. To illustrate the different microstructural components at room temperature as a function of carbon content, a microstructure diagram can be created. At 0% carbon, the microstructure is initially pure iron and therefore 100% ferrite. As the carbon content increases, more and more pearlite is formed until at 0.8% carbon the microstructure is 100% pearlite. At higher carbon contents, cementite precipitates at the grain boundaries. The maximum proportion of grain boundary cementite is at 2.06% carbon, because immediately after solidification the solubility limit is undershot and cementite precipitates. The maximum grain boundary cementite content is 21.5%.